Dear students, today in this class, let us we study about covalent bonds having partial ionic character. It's nothing but polar covalent bonds in detail. According to Lewis, covalent bond formed between the two atoms of the same element is called non-polar covalent bond. This is due to the presence of atoms having same electronegativity. Example, hydrogen, chlorine, fluorine, oxygen, nitrogen, and so on. Covalent bond formed between the two atoms of different elements is called polar covalent bond. This is due to the presence of atoms having different electronegativities. Example like water molecule, HCl, ammonia, carbon dioxide, hydrogen fluoride, and so on. It may be noted that greater the difference in the electronegativity of the bonding atoms, more will be the polarity of the bonds. The example, if I take HF, HCl and HBr, electronegativity of hydrogen in all the cases is 2.1. In case of fluorine, electronegativity is 4. So the difference is more now. In case of chlorine, it is 3. In case of bromine, it is 2.8. Therefore, HF is more polar than HCl and HBr. Coming to the degree of polarity, how it is measured? The degree of polarity is measured in terms of dipole moment. The dipole moment is the product of the magnitude of the positive or negative charge and the distance between the charges. Mathematically, it is given as the dipole moment mu is equal to Q into D. The charge Q is expressed as 10 raised to minus 10 ESU in CGS system, and the distance is expressed as 10 raised to minus 8 centimeter in CGS system. Therefore, the dipole moment mu is equal to 10 raised to minus 10 into 10 raised to minus 8, which will be 10 raised to minus 18 ESU centimeter. This is called 1 dBi. Dipole moment 3.5 dBi means 3.5 into 10 raised to minus 18 ESU centimeter. The SI unit of dipole moment is Coulomb meter. Therefore, 1 dBi is equal to 3.3356 into 10 raised to minus 3 Coulomb meter. Since dipole moment is a vector quantity, its direction is indicated by the sign from the positive pole to the negative pole. In case of hydrogen fluoride, the direction is shown from hydrogen towards the fluorine, which is having 1.78 the dBi. The dipole moment of HCl is 1.07 dBi, HBr is 0.79 dBi, HI is 0.38 dBi. This shows that when we move from hydrogen fluoride to hydrogen iodide, the dipole moment decreases. Similarly, when I take a water molecule and the H2S molecule, the water molecule is having a dipole moment 1.84 dBi and H2S is 0.90 dBi. So, therefore, this shows that water is more polar than H2S. In case of the molecules like carbon dioxide and the boron trichloride, the dipole moment's direction is equal and opposite. Therefore, these molecules have zero dipole moment. Hence, these molecules are perfect symmetric. Molecules with unsymmetrical and bent geometry have resultant dipole moments, whereas the molecules with symmetrical and linear geometry have zero dipole moment, like carbon dioxide, beryllium chloride, boron trichloride, methane, etc. These molecules are non-polar in nature. An ionic bond is the electrostatic force of attraction between the cation and the anion. When a cation approaches anion, the cation attracts the electron cloud of anion and repels its nucleus. Thus, the electron cloud of an anion gets distorted and electron density is pulled in between the nuclei of the two atoms. Just as in covalent bond, electron density is built up between the nuclei of the two ions. Thus, the ionic bond gets covalent character. The ability of cation to distort the electron cloud of the anion is called its polarizing power. And the tendency of the anion to get distorted or polarized by the cation is called its polarizability. The polarizing power of cation and the polarizability of the anion determine the extent of polarization, that is the distortion of the anion. This in turn determines the covalent character of the ionic bond. This can be well understood by applying a set of rules called Fajan's rules. So the Fajan's rules are given below. Number 1, higher the positive charge on the cation, greater its polarizing power to polarize a nearby anion. The increase in polarizing power of the cation increases the covalent character of the bond. Similarly, higher the negative charge on the anion, higher will be its polarizability. The increase in polarizability is accompanied by an increase in the covalent character of the bond. When we take an example, lithium chloride, beryllium chloride, boron trichloride and carbon tetrachloride. Here the positive charge of the cation is increasing from lithium to carbon. Therefore, lithium chloride is more ionic and carbon tetrachloride is having least ionic or more covalent character. Let us take another example, sodium chloride, magnesium chloride and aluminium chloride. Here also positive charge of the cation is increasing from sodium to aluminium. Therefore, sodium chloride is more ionic and aluminium chloride is least ionic. In other words, sodium chloride is least covalent and aluminium chloride is more covalent in nature. Let us take another example, the third one, germanium chloride, tin chloride and lead chloride. Here the valency of germanium is +2, tin is +2 and lead is +2. All the three, they have the same valency, but their sizes are different. So here positive charge of hence these are largely ionic in nature. The same molecules germanium tetrachloride, tin tetrachloride and lead tetrachloride. Here the positive charge of the cation is +4. And these compounds are largely covalent. In other words, the compounds having lower oxidation state are largely ionic, and compounds having higher oxidation state are largely covalent. Let us take another example, HF, H2O, NH3 and CH4. Here negative charge of the anion is increasing from fluorine to carbon. In case of HF, fluorine valency -1, oxygen -2, nitrogen -3 and so on. So as we move from HF to CH4, so covalent character increases. That means HF is more ionic, CH4 is more covalent. Smaller the size of the cation, greater its polarizing power and hence greater its tendency to form covalent compounds. Let us take some examples. Beryllium chloride, magnesium chloride, calcium chloride, strontium chloride and barium chloride. The positive ions belongs to the second group in the periodic table. The size of the cation increases down the group. Since beryllium is having smallest size and hence having great polarizing power, therefore it forms covalent compound. As a result, beryllium chloride is largely covalent and barium chloride is largely ionic in nature. Larger the size of the anion, more will be its polarizability and hence greater will be the tendency of the anion to form covalent compounds. For this, let us take an example, calcium fluoride, calcium chloride, calcium bromide and calcium iodide. The negative ions belongs to the class halogens in the periodic table. The size of the anion increases down the group. Fluoride ion has least polarizability due to highest electron affinity. Therefore, calcium fluoride is largely ionic and calcium iodide is largely covalent in character. Let us take one more example, sodium fluoride, sodium chloride, sodium bromide and sodium iodide. Here sodium fluoride is largely ionic and sodium iodide is largely covalent in character. So ionic character decreases from HF to Hi. Similarly, ionic character decreases from aluminium fluoride to aluminium iodide. In other words, covalent character increases from aluminium fluoride to aluminium iodide. The cation with Ns2p6d10 configuration has greater polarizing power than the cation with Ns2p6 configuration and hence has greater tendency to form covalent compound. Let us take an example of cuprous chloride and sodium chloride. In case of cuprous chloride, the cuprous ion has the configuration 3s2, 3p6, 3d10 and the Cu plus has 18 electron in the valence shell and sodium ion has 8 electrons in the valence shell configuration. Hence, Cu plus has greater polarizing power to polarize chloride ion than the sodium ion. As a result, cuprous chloride is covalent in nature and sodium chloride is ionic in nature. Let us take another example, sodium iodide and silver iodide. Due to 18 electron valence shell configuration, the polarizing power of silver ion to polarize iodide ion in silver iodide is so great that it makes silver iodide covalent. Therefore, sodium iodide is ionic and silver iodide is covalent. The next, polarizing power of cation increases from left to right in a period of the periodic table. Hence, tendency to form covalent compounds also increases in the same direction. Polarizing power of cation decreases from top to bottom in a group of the periodic table. Hence, tendency to form covalent compounds also decreases in the same direction. The polarizability of an ion decreases from left to right in a period of the periodic table. Hence, tendency to form covalent compounds also decreases in the same direction. The polarizability of an ion increases from top to bottom in a group of the periodic table. Hence, tendency to form covalent compounds also increases in the same direction. Now let us study how to calculate the percentage of ionic character in covalent compounds. The dipole moment values help in calculating the percentage ionic character of polar bonds. It is the ratio of observed dipole moment or experimentally determined dipole moment to the dipole moment for the complete transfer of electrons, that is 100% ionic character. Mathematically, it is given as percent ionic character is equal to observed dipole moment or experimental dipole moment divided by 100% ionic dipole moment into 100. Let us take some of the problems based on this equation. The first problem, the observed dipole moment of HCl molecule is 1.03 dBi. For complete transfer of electrons, the charge on H plus and Cl minus ions would be equal to 4.8 into 10 raised to minus 10 ESU, and the bond length of HCl is 1.274 into 10 raised to minus 8 centimeter. So based on this, we have to calculate the dipole moment of complete transfer of electron, which is nothing but mu is equal to Q into D. Substituting the values of Q and D, we get mu ionic 6.12 dBi. However, the observed dipole moment is 1.03 dBi. Therefore, percent ionic character is equal to observed dipole moment divided by ionic dipole moment into 100, that is 1.03 divided by 6.12 into 100, that is 16.83%. Let us take another example. The dipole moment of lithium hydride is 1.964 into 10 raised to minus 29 Coulomb meter. And the interatomic distance between lithium and hydrogen in the molecule is 1.596 angstrom. Calculate the percent ionic character in lithium hydride. The bracket, the charge Q is equal to 1.602 into 10 raised to minus 19 Coulomb. So first we have to calculate dipole moment of the ionic, that is 100% ionic, that is equal to Q into D. The Q is 1.602 into 10 raised to minus 19 and the distance is 1.596 into 10 raised to minus 10 centimeter, the Coulomb per meter. The value comes to be 2.557 into 10 raised to minus 29 Coulomb meter. Percent ionic character is equal to observed dipole moment divided by ionic dipole moment into 100. That's equal to 1.964 into 10 raised to minus 29 divided by 2.557 into 10 raised to minus 29 into 100. That gives 76.8%. The students, this is how you have to calculate the percent ionic character in these molecules. So this slide shows about the Fajan's rules. So what is the polarizability and what is polarizing power? So here this slide also shows the polarization of cation. So it increases from calcium to magnesium and further beryllium. So whereas the ionic character and thermal stability increases in this direction. Polarizing power of an ion increases from fluoride towards the iodide, and therefore solubility in polar solvent increases from silver iodide to silver fluoride. So this slide shows the polarizability and also how the Fajan's rule, the covalent character in ionic compound. So it increases and decreases across the period and along the group. So this is the slide. It shows how to calculate the percent ionic character in various molecules. So the students, go through this much and try to learn about the ionic character in covalent compounds. Thank you.